Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see shear of open section beam. So on open section beam, how the shear will be there. Okay, so our lecture topic will be shear of open section beams. Okay, so now let's start. The open section beam of arbitrary section shown in figure 1, okay, that is shear loading of open section beam, supports shear load Sx, okay, Sx along the x-axis and Sy along the y-axis, that is, so Sx and Sy such that there is no twisting of the beam cross section. So means you have to apply the Sx and Sy, but twist should not be there. Suppose we are applying the force here, right? Now if we will apply the force, definitely this will move or that will rotate. So if along the x-axis, if you will apply the force like this, then it will twist. Along the y-axis, then this will twist in this direction. The twist should not be there. That we have to take care, is where we have to apply the force. So once we will apply the force at the shear center, okay, then there is no twist if we will apply the force along the x-axis and along the y-axis, or you can say where there is no twisting, the force where is acting and there is no twisting, that is the point of shear center. Okay, so for this condition to be valid, the shear load must both, that Sx and Sy, pass through a particular point in the cross section known as shear center. So if this will pass through the shear center, that Sx and Sy will pass through the shear center, then there is no twist. Okay, that twisting will not be there. Since there are no hoop stress, because it's an open section, this hoop stress, it won't be there. For the closed one, already we discussed that, just you have to add the hoop stress, that Qs, 0. So here this one is open, so there is no hoop stress. So means just remove that term, remaining thing will be same. Okay, the shear flow and direct stresses acting on an element of the beam wall are related by how? That delta Q by delta S plus T into delta sigma Z by delta Z equals to 0. So this you have to remember. So now just see, this part is open from this inside, right? And this is the thickness of this open section, whatever, either cylinder or anything, whatever is there. Just here it should look like cylinder. So in any section, that thickness, whatever, will be there. Along the shear point, just here at Sx and Sy is acting, so no twist will be there. Okay, so now what is the moment? Moment is force per unit area, right? Sorry, force into, so moment will be what? Force into perpendicular distance, right? What is force? Sigma into A into that distance. So just assume D. Or we can say, suppose we are finding F, then F will be what? F will be moment by perpendicular distance, right? So if we are finding that changiness, so delta F equals to delta M by that perpendicular distance. So here distance we are taking in terms of Z. So and Sx is F. So Sx will be equals to what? Delta M V by that, just for vertical moment. Okay. So delta M V by what? Delta Z, because along the Z axis we are taking. So this will be your Sx. Okay. Similarly and so on, like same for MV, that delta Sx we found, now Sy. Okay. So on this expression becomes, now we are finding for what? Delta sigma Z by delta Z, right? So just see here, Sx Ixx minus Sy Ixy. So here you have to remember one thing, that what? This first term if you remember, right? Then second term according to that you can write. So just see here what is there. So Sx Ixx minus, so x here is there, so Ixx also. But once y is there, that time Sy Ixy by this denominator will be same for both the cases, Ixx into Iyy minus I square xy. And if Sx is positive first term, that Sx is positive, so multiplied by x. Plus, now we are taking that Sx plus Ixx, now here Sy into Iyy minus Sx Ixy. So see here, it's almost, you can say it's a similar and easy to remember. How? If first term you are taking Sx, then Ixx will be there, minus Sy with different one, sy, xxy. Now in this case, sy we are taking, so with sy, iyy, and minus with sx different of that one, that is ixy. Here first term, that sx, this term is positive, so multiplied with x. So here y term is positive, so multiplied with y. This I am telling just to remember. It's not that formula, okay, this one is there, that's why it's multiplying y. How to remember and to check that whether you wrote correct formula or not. Okay, divided by what? Just both of same, that ixx into iyy minus square of that different, that ixy. With this also ixx, iyy minus I square xy. Okay, substituting for delta sigma z by del z, where here, right? So what we have, del q by del s plus t into del sigma z by del z equals to 0. So substitute here del sigma z by del z equals to 0. So what we will get? This one, or we can write this as del q by del s equals to t, or minus t del sigma z by del z. After taking this to this side, simply thus this term becomes minus, or take this to this side, then this becomes minus, anyone. So which one we have taken minus? That kept dq by ds positive, then the other term that side. So after substituting that sigma x value, right, so this is sigma x by sigma z. So and that into t will be there. Just see here, that t term will get multiplied. So here t term will get multiplied with both the term. Okay, because why? This into t is your t sigma z. That's other side of the equal to part. Now multiply with this t to here also, here also. So this becomes tx, and here it becomes ty. So just say tx, ty. Okay. Now this is for that sectional part. Now for the overall, what we have to do, we have to integrate for the entire exponent. So integral of this 0 to s del q by del s into ds, which is equals to what? This one, because of this minus sign. So minus of sx ixx. Okay, this minus is here common. So after that, just well, sx ixx minus sy ixy, ixx iyy minus I square xy. Just same here. This term, whatever is there, just you have to write, or just you got whatever here. Into close integral of 0 to s tx ds minus same again sy iyy minus sx iyy by ixx iyy minus I square xy into close integral of dy dx. So this is the constant term, right? That's why it's out of integration. This also is constant term. That's why out of integration from this one, right? Now let's see here what we can say. Now after this, both are same. So this one. So qs will be what? After integrating this, we will get qs. So qs will be minus of sx ixx minus sy ixy by ixs iyy minus I square xy. Then 0 to s tx dx minus sy, same, just repeat here, sy iyy minus sx ixy by ixx iyy minus I square xy, and into integral of 0 to s dy ds. Okay, now because of the axis of symmetry, if symmetry is there, means ixy will be 0. So if we will take along the axis of the symmetry, then ixy will be equals to what? 0. Okay, so now just substitute wherever ixy is there, that as 0. Okay, so let's substituting ixy as 0, what we are getting. So first I am simplifying this term. Okay, so sx ixx minus sy ixy by ixx iyy minus I square xy. Okay, so now iyy. Now what we are doing, we are putting ixy as 0. So sx ixx minus sy into ixy is here, so 0, divided by ixx into iyy minus, okay, I square x, so 0 square, that is 0 square. So from here what we can write as x ixx by ixx into iyy. So now ixx cancel. So what we get here, sx by iyy. So let's see how we will check. Sx we are finding and we are getting in terms of iyy. Similarly for this side. Okay, so now here we will get sy by ixx. Okay, so sy by ixx. Same way you can just put ixx 0. So this will be 0. So this term will get removed. This term again will be 0. So now what is left? Sy, Iyy, Ix, Iyy. So Iyy cancel. What you will get? Sy by Ix. So now this is the cube. Yes, okay. Okay. So now from the above equation of the shear flow, that is from here, right? The shear flow distribution in the cross section of an open section beam is based on the equilibrium equation that must be equal to 0. The thickness T in this equation refers to the direct stress carrying thickness TD. So in this case, what happened? This T will be is equals to TD. Above equation may be therefore be written as just so wherever T is there, just replace to TD as the TD. So QS equals to minus of SX IXX minus SY Iyy by Ixx into Iyy minus I square xy 0 to S TDX into DS minus SY Iyy minus SX IXY by Ixx Iyy minus I square xy integral of 0 to S TD. So again here just T got replaced by TD DS. Okay, in which TD equals to 2T if the skin is fully effective, means total skin if you are considering, right? That time TD will be equals to T at thickness in carrying direct stress, or TD equals to 0 if the skin is assumed to carry only the shear stress. So if we are just in the starting also we had seen that we are carrying that skin is carrying only the shear stress and boom is carrying only the direct stress. So if that skin is carrying only the shear stress, that time TD will be 0. If T that carrying the full effect is there, then that time TD will be equals to T. Okay, so now above equation makes no provision for the effect of boom. Means what? After this there is no effect of boom, hence we can just resolve, which cause discontinuities in the skin and therefore interrupt the shear flow. Okay, so once that skin that this will be there, that boom, right? For the effect of boom, definitely discontinuities will be there, right? Because in between we are adding the boom. Okay, therefore interrupts the shear flow. Consider the equilibrium of Rth boom. Rth means any number of time, like 4th, 5th, whatever the you want, first, second. So depending upon how many are there, just take any one and put the R value. Like for first, if you wanna find, then that R becomes 1. For second, R becomes 2. Okay, so for fifth, R becomes 5. And the elemental length of beam shown in figure, which carries shear load Sx and Sy acting through its shear center. Shear center means what? There is no twist or 0 twist. If twist will be there, then the equation will be different. Then we have to include the twist also. But here, what we are doing, we are not including any twist. That's why we are applying the force at shear center. Okay. So now you see, this is the boom after changing that whatever the center and spots are there here, right? So these are the booms. So take any booms. They have taken this as Rth boom, whose coordinate is xr, yr. Now this we have to, so after idealizing this one, so once this one is there, so elemental length of shear load of open section with boom, right? Now for equilibrium of the boom element is here. The same way first what we had seen, okay, to idealize that one, then we found sigma 1, that b1 and b2. Same here we have to find b1, okay, because only we are considering for one boom, that Rth boom, so that is br for first boom, b1. Okay, so now here this will be there. So in that what we have to do, just see how these forces will be there. So Q2 is acting like this and Q1 is acting in this direction. Sigma z is acting in this direction. So sigma z plus del sigma z by del z into dz will act in this direction. Right. Now again for the what? That should be equilibrium, is all forces acting this side should be equal to all the forces acting in that side. Just equate it. Okay, so let's see what will be the equation. This shear load produce direct stresses due to bending in the boom and skin, and shear stresses in the skin. So just here, shear load produce direct stresses due to bending in the boom and skin, and shear stresses in the skin. These shear loads are there. Suppose that shear flow in the skin adjacent to Rth boom of cross sectional area BR. Just assuming that R is there, so just put everywhere R. Okay, and then according to that which boom you require, just put, suppose for B1, the boom 1, then B1. Okay, so now again it's the same. So sigma z, so just see here, this side should be equals to this side, or this side minus this side should be equals to 0. Okay, so first taking this side, sigma z plus del sigma z by del z into del z into Q2 BR, right? Because Q2 is acting in this direction, and minus Q1 into BR minus sigma z. Okay, this here sigma z plus this into BR minus sigma z BR plus Q2, because that direction it's acting, so plus Q2 del z minus Q1 del z equals to 0. So just from this side, which simplifies, just expand this one and simplify. So let's see, expand that one. How? So sigma z plus, so I'm multiplying here, means this opening this bracket simply, sigma z BR, okay, plus del sigma z by del z into del z, okay, into BR, okay, minus sigma z BR plus Q2 del z minus Q1 del z equals to 0. So now sigma to BR will get cancelled, right? Now what we will get? Del sigma z by del z into del z into BR, okay, then plus Q2 del z minus Q1 del z equals to 0. Take these two terms this side. So del sigma z by del z into del z BR is equals to what? This will go, this side becomes positive and this becomes minus. So Q1 del z minus Q2 del z. Okay, now taking del z common from here. So del sigma z by del z into del z into BR equals to what? After taking common del z, Q1 minus Q2. Okay, so now this del z get cancelled. So now what we have? Q1, okay. So from here what we have? Q1 minus Q2 equals to, just taking this side, so minus of that Q1 minus Q2 will be equals to del sigma z by del z into BR, or if you want to write in terms of Q2 positive, then Q2 minus Q1 will be equals to minus of del sigma z by del z into BR. Okay, so this will be our Q2 minus Q1. Now just substitute del sigma z by this value. Okay, so that already we found that del sigma z by del z, that is here. So there we found in terms of first step we wrote that in terms of moment. So moment, or you can use in terms of stress. So here this is in terms of moment, and saying here this is in terms of what? Shear, that shear load Sx, right? So don't get confused, just already we had seen these two equations. From those two equations you have to substitute here. Alright, so this in terms of moment you will get, and this in terms of shear load. Okay, now equation gives the change in shear flow, that is Q2 minus Q1 is change induced by a boom which itself is subjected to direct stress. So means that itself is experiencing load what? Sigma z into BR. Okay, now each time a boom is encountered, the shear flow is increased by this amount, so that if at any section, sorry, any distance as around the profile of the section and boom have been passed, the shear flow at that point is given by, means whatever is there, just you have to take all the, that's just you have to take the summation of that one. So just see here, means these things will be same, because the T ds and Td into x into ds, that also will be same for all the parts. Only the things, how many booms are there, that many booms into that distance, that boom area into that distance from that perpendicular distance from this one. So if suppose like in this figure here, how many are there? 1, 2, 3, 4, 5, 6. 6 booms are there, right? So for if you will write this overall for this one, then what happen here? This will be okay. So this equation will be what? Minus Sxixx minus Syiyyy by Ixxiyy minus I square xy. Okay, this into 0 to Stdx into ds plus sigma r equals to 1 to 6, because in that figure 6 booms are there, right? So 6 BRXR, meaning what? For this I'm just writing sigma means what? Summation. So from 1 to 6 means B1 R1 plus B2 R2 plus B3 R3 plus B4 R4 plus B5 R5 plus B6 R6. Right. So for this term alone only, if this you have to add. Okay. So just find the boom area of this total, add, and then just substitute here. Then you will get for the n number of booms. Right. That's why we have just chosen one, and now whatever is there for one, first B1 x1, for 2 B2 x2, and then take sum of all this sigma term, you will get the total boom area, and then just do same procedure. So that's why from the starting itself, instead of finding 1, 2, 3, we assume that BR as the first, and according to that we derive for that one, and later what we are doing, we are just writing in the form of summation so that we can just add as many as number of booms are there. Okay, so this total QS will be equals to the first term minus this second term. So this is BR XR, this is BR YR, right? Because this is the with Y term, so BR YR. So just again TD Y DS. So here Y term is there, so BR YR. Here X term is there, so here BR XR. Okay, so now arguments identical to those in the shear of open section beam apply in this section. So same, just whatever is for that is there, that also. Thus the shear flow at any point around the cross section of a closed section beam comprising booms and a skin of direct stress carrying thickness TD is the shear. This for the closed section beam. This hoop stress is added here. Remaining everything is same. Okay, just so this is for what? Open section, right? The dimension, so that compared to the previous one. Okay, shear loading of closed section beam. So this whole thing will be same, only this hoop stress will get added, right? Remaining things are same. Note that the zero value of the basic or open section shear flow as the cut in a skin for TD equals to this. TD is this one, TD is subscript. TD equals to 0. That thickness we are seeing is the skin is carrying only the shear stress, not direct stress. Extend from the cut to the adjacent boom. So wherever the cut is there to the adjacent boom is from here, or where suppose cut is here, then here to here, whatever the wherever the boom is there. Okay, so now this is over. Okay, so let me just recall once again quickly. Okay, so now we are finding for shear of open section, that's shear stress distribution of open section beam. So we have applied load Sx and Sy, okay, so that the twist should not be there. So for twist, that must be act through the shear center only, then twisting won't be there. So this Sx and Sy is acting along the shear stress. And since it's a what open section means there is no hoop stress, so just we take hoop stress term 0. That's why in last slide I showed you, even if hoop stress will be there or that close will be there, then just you have to add that hoop stress term. Okay, so for flow direct, this will be del Q by del S plus T into del sigma Z by del Z. Now what we will do, we will find the del sigma Z by del Z value, and then we will substitute back here. How to find the shear? That del MV by del Z equals to Sx. So in terms of sigma, del sigma Z by del Z equals to Sx Ixx, means shear load along x-axis into the moment of inertia in Ixx, that xx direction, minus Sy Ixy by Ixx Iyy minus I square xy into x. Similarly for y part, Sy Iyy minus Sx Ixy by Ixx Iyy minus I square xy into y. Substituting for del sigma Z by del Z in the previous equation. So what we will get, or here if you will take this side, this becomes negative. So del Q by del S equals to what? Minus of T del sigma Z by del Z. Now put here sigma Z by del Z here. Right? After substituting, we will get this equation, right? Integrate that equation. After that, what? After integrating, substitute because of the symmetry, put Ixy as 0. So after substituting Ixy 0 in this, what we will get? Qs equals to this one. Okay, so now for this open one, so just whatever the QS is there, that T in terms of, instead of T, just write in terms of TD. So when TD equals to T, means the total surface is effective, means fully effective skin is there. And if TD equals to 0, means that is carrying only the shear stress. So that two things you have to remember. If TD is 0, means skin is not carrying any direct stress, only it's carrying the shear stress, and TD is means it's a fully effective. Okay, so for now, for this we have to find, means what we will do, take any one boom, find for that one, and then in similar way you can say that okay, for all others we can find. So now just taking any boom that is given name as Rth, instead of B1, R1, R2, you can just Rth boom. So we will find that one generalized one, and then we will put the value of R like 1, 2, 3, we will get for all. So here that is the equilibrium of that one. So for equilibrium, what should be there? The total acting this side should be equals to this side, or this side, whatever the forces is acting, minus this side should be equals to 0. So take here. So after finding this, that should be equals to 0. Okay, take Q1, Q2 that side, right? And then simplify. After simplifying this one, substitute here del sigma z by del z. So after substituting here in terms of M, and this is in terms of S, X, that is shear load, this in terms of moment, and here no, any same will be there because Sx equals to del M by del Z. But here this moment term is there. So after substituting, what we will get? The distribution, that difference of this Q2 minus Q1, right? How much change will be there? Okay, so after that just substitute here that Qs what? Okay, for n number of boom. Okay, if n number of boom is there, then just that will be R equals to 1 to n. I showed you also for 1 to 6, because in that figure 6 booms are there. So we will be B1 R1 plus B2 R2 plus B3 R3 so on, B6 R6. So depending upon how many number of booms are there, that you have to just substitute here. Okay, and for that was for this. So this is for the open section. Now if it's a closed, then in the starting we had seen that hoop stress is 0, but for closed, hoop stress will be there. So just in the same, we have to add the hoop stress term, that Qs comma 0. So this is the hoop stress that will be the for closed section beam. Okay, so this is your introduction, which you can just refer Maxon book 4th edition. Okay, thank you. If you have any doubt, you can just complain, that you can just comment on the videos itself, or you can contact me regarding your doubt. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.